Okay, welcome back. Today we're going to complete our derivation of Gauss's remarkable theorem. I have it written up here, at least its formulation in the case when the ambient space is Euclidean. When the ambient space is not Euclidean, it looks a little bit more complicated, and you'll understand the way in which it looks a little bit more complicated. Along the way, these two relationships are actually siblings. They'll arise at the same time. The other sibling is the Codazzi relationship that you see over here. So this relationship is also only valid when the ambient space is Euclidean. Let's see what it's saying. What it's really saying is that this symbol is symmetric in alpha and beta. It's symmetric in its first two indices. So if we just looked at this symbol on its own, we would know that it's symmetric in beta and gamma because the curvature tensor is symmetric in beta and gamma. But we learn a lot more. We learn that it's also symmetric in the first two indices, and it's therefore completely symmetric with respect to all of its indices. That's Kadasi equation, and it only holds in this form when the ambient space is Euclidean. However, our derivation will be in a slightly more general setting. We'll assume that the ambient space is actually Riemann. We don't need to assume that the Riemann-Christoffel symbol in the ambient space vanishes. And what Gauss's remarkable theorem really is, what these two as a pair really are, is the relationship between the ambient and the surface Riemann-Christoffel tensors. Now, we've done a number of similar exercises. We've related the ambient and the surface Laplacians. We've related the ambient and the surface Christoffel symbols. Along the way, we also derived this nice relationship, which applies to the surface commutator when applied to a tensor with an ambient index. And we discovered that the ambient Riemann-Christoffel tensor is what plays the key role in that relationship. It's the kind of a projection of that relationship. And of course, we were given this one for free. And the ones that we focused on in the last couple of lectures had the operand with an upper index. And I left it as an exercise for you to derive what happens when the operand is a lower index, which is more convenient than deriving this form. Of course, it could have been done the other way and then the index lowered later, but it's a little bit nicer this way. And there are only a couple of differences, as I'm sure you've discovered. There's a minus sign, and also the contraction happens on the first index of the Riemann-Christoffel tensor. So with all this, we're ready to go. What we need to think about is how are we going to relate the surface Riemann-Christoffel tensor to the ambient Riemann-Christoffel tensor. We really need to find a way where they would be both prominently featured. And of course, this one can be expressed as a function of Christoffels and its derivatives. This one can be expressed as a combination of its Christoffels, the ambient Christoffels, and its derivatives, their derivatives. But that's a long and an unappealing way to go. So I'm going to show you a trick which works quite often, which we haven't used in the videos, but in the book it's used all the time. And it's this trick. It's really not a trick, but if we just need to somehow be able to use both of these identities in the same relationship. And the way you do it is by saying, well, right now they're just two completely independent things, t sub k and t sub gamma. But what if t sub gamma? Let's consider a arbitrary t sub k, and let's let t gamma be a projection of t sub k. So let's define t gamma as t sub k projected. And let's apply this relationship to this combination. So of course, here's what's going to happen. Because we're applying this relationship to, on the one hand, this guy, we'll be able to write that it equals this right-hand side, where t sub omega can, of course, once again be expanded in this way. That will be the left-hand side. On the other hand, we can plug in this product in here and apply this commutator to the product and use the product rule. And somewhere along the way, we'll get the commutator applied to t sub k, and then we'll be able to use this formula. And then equating the right-hand side and the left-hand side, we'll be able to relate this Riemann-Christoffel tensor to this Riemann-Christoffel tensor. it's going to be a lot of derivations. So I'm going to keep our target on top of the board. I will erase this, we'll remember them. And as soon as you see, oh, I see how this appears, and oh, I see how this appears, you might as well just turn off the video and complete the derivation on your own. It's very enjoyable. So that's what we're going to do. What we're about to do is apply this commutator to this product. And then we'll recall that on the left-hand side we have this, and on the right-hand side, well, we'll just see what we have. But it will somehow end up relating this to this, and maybe some other terms, of course. Okay, so let's take a look at how that happens. I'm about to erase the board and start the calculation by applying this commutator to this product, and I expect I'll have to write small. So let's try and do it. Okay, what I have written here is half the commutator that we were talking about. We're going to figure out half the commutator, and then we'll just see what happens when you switch alpha and beta and subtract one from the other. So by now I expect that everybody's experienced with these fundamental calculations. So some of the elementary steps I will absorb into one larger step, and hopefully you can keep up. And if not, there are plenty of lectures to look back upon and see where all of that comes from. Okay, so first we'll apply the chain rule, of course. And we have this, and then in parentheses, it's the surface derivative applied to t sub k, leaving the shift tensor unchanged, minus tk, t sub k unchanged, plus this derivative applied to the shift tensor, which of course by the fundamental formula equals the normal times the curvature tensor. So n k b beta gamma. B beta gamma. And this completes the first step of our analysis. Let's continue with the second step of our analysis, which will be applying the product rule to this whole thing. So we're going to have 5 terms, 2 from here and 3 from here. So let's discover what those terms are. The first term is, of course, this. It's the derivative applied to the derivative of t sub k, where the shift tensor is left alone. Let's make it the right size. zk gamma plus the term where this is left alone, and the derivative is applied to the shift tensor, which of course produces the normal times the curvature tensor. The normal times the curvature tensor alpha gamma. Okay, moving on to this term, excuse me, with a plus sign. Moving on to this term, we have the derivative first applied to tk, and the other 2 terms are unchanged, b beta gamma, plus the derivative applied to n sub k. So maybe this plus was a little bit premature, you'll see in a moment why, but it's t sub k. And what will go in here is the derivative sub alpha applied to n k, which by Wien-Garten's formula equals minus z I think omega, we need a new letter, b omega alpha. That's Wien-Garten's formula. It's going to go in here. So this plus is really a minus tk, excuse me, with a k here. So z k omega b omega alpha b, excuse me, That's right. B, beta, gamma. And then finally a third term. Excuse me about that. And then finally a third term where the derivative applies to the plus tk and k curvature tensor. Grad the covariant derivative sub alpha applied to b, beta, gamma. All right, so these are the 5 terms. We have completely expanded and simplified this expression. And what we'll now need to do is subtract, to get the commutator, subtract from this, the same thing with alpha and beta switch. So now you see how the formulas that we had on the board before really come in handy, because what we'll have here is the commutator applied to T sub k. That will involve the ambient Christoffels. And just to save space, it's at this point that we'll assume that the ambient Christoffels are 0. In other words, we're assuming that the ambient space is Euclidean. If you're following this, trying to derive these expressions on your own, you should certainly not do that because you have more space than I do, and you should derive these equations in their full generality, or at least fuller generality. In other words, assuming that the ambient space is not necessarily Euclidean, but we'll assume that it's Euclidean. So this term, because it's proportional to the ambient Riemann-Christoffel tensor, will vanish. So this is gone. Now let's look at this term. This is an interesting term. It's, of course, not symmetric in alpha and beta, but if alpha and beta in this term are switched, which is the term we would get when we're considering the opposite starting point, it becomes this term. Do you see that? And of course, this term becomes this term. So individually, they're neither symmetric nor skew-symmetric nor anything else in alpha and beta, but combined, they're symmetric in alpha and beta. So when we form the full commutator, these 2 terms drop out as well. So we're only left with these terms and this term. Each one will have to switch alpha and beta. And now I think you're beginning to see where this will come from and where this will come from. And it happens in a very beautiful way. All right, so let's do that in the remaining space. I'll have to duck a little bit, but I want to complete everything on the same board. But let me just be very liberal here and just cross out these terms. They're not 0 on their own, but in the commutator context, they are 0. Now let's talk about the left-hand side. This, what we have here, when we combine it with the opposite term, is the commutator applied to T gamma. T gamma, a simple tensor with a single surface index. So we know what that is. That will be the surface. So let's make sure we're starting a new chain. Okay, so what this will be is the surface Riemann-Christoffel symbol with omega, minus sign, omega, gamma, alpha, beta, T sub omega, which of course is T sub k, z, k, omega. This is T sub omega, so we wrote down the rule for the surface commutator applied to T sub gamma, which is an object with 1 surface index. So that's the left-hand side. That's kind of wonderful. Equals. All right, let's see what we'll have here. Minus. Let's leave this outside. Minus T sub k, z k omega, z k omega. And then in parentheses we have b omega alpha, b beta gamma, minus the same thing with alpha and beta switched. B omega beta, B alpha gamma, alpha gamma. Okay, that takes care of this term. Then I kept the let's keep the minus sign out here, not forget about it. We'll later cancel it with this minus sign. But now we have to write plus t sub k and k. And in parentheses we have this term minus the term with alpha and beta switched. So this term, b beta gamma, minus the same thing with beta and alpha switched. Alpha, gamma, fit perfectly. Okay, now we have to, it's kind of amazing how it worked out, that I didn't have to rename any indices so far. So we now have to take advantage of the fact that t sub k is completely arbitrary. T sub k can be factored out from the whole thing, and then it's just a little bit of linear algebra reasoning to convince ourselves that if this identity is valid for an arbitrary tk, then whatever quote-unquote matrices t sub k quote-unquote multiplies, it still remains valid. Okay, excuse me, whatever it multiplies, those matrices must be equal. So this expression actually remains true with t sub k erased, because it's the matrices, what's left is the matrices that t sub k multiplies. So let's actually do what I just said. Erase t sub k, and what we'll have left is the identity that we're actually looking for. Okay, so erasing t sub k, I will erase both t sub k and zk omega, and then move zk omega closer. Zk omega. Erasing minus t sub k here, saving the minus sign. Excellent. And erasing t sub k here. And what we have is a relationship that has nothing to do with t sub k, has only to do with the surface and the way in which it is embedded in the ambient space. That's fantastic. And we actually have a very valuable equation. Actually, something more general than either the remarkable theorem or Codazzi equations, relationship it's called, Codazzi relation. What we actually have is both of these equations combined and coded into a single equation. We will find out that in a moment that the Codazzi relation is the quote-unquote normal component of this equation, and Gauss's remarkable theorem is the tangential component of this relationship. We'll see how to, I'll show you, you can probably see there's nothing really to show, how to extract these two beautiful relationships from this combined relationship. So this combined relationship has a very appropriate name. It's called the Gauss-Codazzi equation. Very appropriate name. Okay, Gauss-Codazzi equation, that's the more general one. Now, I will just say it, because saying it is easier than actually doing it in this case. So from this more general equation, if you want to extract these two equations, let's start with Codazzi relationship, Codazzi relations. What you have to do is take this identity and dot both things, forget about dot, multiply both things by n sub k, which means implies contraction on k. And of course, because the shift is quote-unquote orthogonal to the normal, this vanishes. This term vanishes for the same reason. Here we have, I meant n sub k with a lower index k. We have nk and k, which of course is 1 because n is unit length. And what we have left is that this equation equals 0. So the Codazzi relation has been derived. So you see how to get Gauss's theorem of Egregium out of this expression? Of course, it'll later require some index renaming, but basically what you need to do is dot both sides of this equation with z, let's see, z sub k and delta, because we need the letter delta somewhere, and here as well, z sub k delta, and let's squeeze in z sub k delta here as well. So what will happen now? What will happen now is this term is 0 because these two are quote-unquote orthogonal. And of course you must remember that this combination is the Kronecker delta, delta omega, which we'll just rename this index omega is the delta. That's because this is delta, delta omega. So of course it'll just go away. Go away. Renaming this omega into delta. Okay, let's, while we're at it, cancel the two minus signs. You no longer need the parentheses. And the same thing will happen on the left-hand side where omega will become delta. Omega will become delta. And we essentially have Gauss's remarkable theorem. The only thing, sorry about that. Gauss deserves better. Okay. The only thing that's left to do is to lower the index delta. Let's do that. Not just say it, let's actually just do it. Delta. 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 And what we have here is the exact same thing as we have here, subject to a little bit of renaming that you have to do. You have to switch alpha, beta, and gamma and delta, and then as I'm looking at it, you also have to switch gamma and delta. So up to renaming of indices, this identity is Gauss's theorem of Egregium. So there you go. The moment that I've been waiting for, well, I haven't been waiting for the moment of reaching this conclusion. What I've really been looking forward to is doing this calculation, which to me is exhilarating. And I don't do it anymore, but I think I've done this calculation 10 times in my life, just because I enjoy the dancing indices and how everything works out perfectly, and how you're guaranteed a perfect geometric intuition and something meaningful and valuable at the end of the calculation, whether or not Gauss got there first, and whether or not it's important, and whether or not it's significant, or whether or not you'll be recognized for it. What you'll end up with is beautiful and meaningful. And that's what we got a chance to do today. So there you go. Congratulations to all of us. I think I will now not go further in tensor calculus until I've cleaned up a few things that I promised to fill in, and that's what I'll probably do over the next couple of lectures. Okay? Thank you very much, and I'll see you next time. Thank you.